So our next family, our second last family, is the carboxylic acids. So carboxylic acids end in anoic acid. That's the anoic acid. And the functional group for carboxylic acids is C double bond O and then an OH group at the bottom. And again, this OH is an O bonded to a H. So this is what we're looking for. So if we run down through the first couple of compounds, so the first one you're going to have is methanoic. So methanoic acid. And methanoic acid again is just got one carbon. So it's one carbon and you have a double bond O and an OH and then just a H on the other side of it. So COOOH. This is written as HCOOH. So this particular part here, that is the functional group for the carboxylic acids. If you move on to the next one, after methanoic acid, you're going to have ethanoic acid. And ethanoic acid is the same, except we've got two carbons this time. So we've got a carbon, double bond O, and OH, and then it's surrounded by hydrogens. So when you're writing this out, it's going to be CH3, which is the first group. So our CH3 is that particular part there, and then you write your COOH at the end. So that's your ethanoic acid. Then you move on to the next one, which is propanoic acid. So again, 3 carbons this time, propanoic acid. So we got 1 carbon, 2 carbons, 3 carbons. And at the end, you have to have a double bond O and an OH. And this is your propanoic, so you surround these carbons by your hydrogens. And the way you write this, again, is C2H5. And then COOH. So the C2H5 is obviously this particular part here. And then the COOH is the part at the end. And then finally we get on to what's called butanoic acid. So butanoic is going to have 4 carbons this time. But there's also an isomer of butanoic acid. So let's have a look. 1, 2, 3, 4. And that is my noisy children screaming and shouting in the background, annoying me, making me wish I was still in work. Right, so let's fill in all these single bonds. Okay, so butanoic acid, 4 carbons. So if we're writing the 4 for this, you're going to be C3 and H7 and then COOH. So remember, this is butanoic. Sometimes what happens is students see the C3 and they think it's propanoic straight away, but don't forget there's another carbon there, so that makes your 4 carbons. That's something a mistake that's often made. So that's butanoic, but there is another arrangement for this, for butanoic acid. There's an isomer. So one of the way we often create isomers is we lob off one of the carbons and create a methyl group. So what we can do is drop from 4 carbons back to 3 carbons, put in your carboxylic acid functional group, and then stick in a methyl group along the way. Pop in your hydrogens all the way around, and you should be able to see that there is 3 carbons and 7 hydrogens and another carbon and an OOH group there. So this is not butanoic acid, obviously, because it's the longest chain is 3 carbons. So if the longest chain is 3 carbons, this is going to be propanoic acid. So propanoic acid, I'll just put that down there. And then there is a methyl group on the second carbon. So again, we're numbering from this side, that's 1, that's 2, that's 3. So we have 2-methyl propanoic acid. And it's important to note that they are isomers of each other. Okay, so they're the main structures of the first bunch of carboxylic acids. So we've got to look at some uses of these. So uses is next. When we're looking at the uses of the carboxylic acids, the first one we're going to look at is methanoic. So methanoic acid is, it's not really a use, but methanoic acid is found in the stings of ants and nettles. So your nettle sting, that's what it contains. And ant stings as well. And I think wasp stings too. Ethanoic acid, which is the next one. So ethanoic acid, we've done an experiment on this, is vinegar. So that's one of the uses for that, for baking. And it's also found in paints and things like that. And then finally, propanoic acid. Propanoic acid. And indeed, there's another one called benzoic acid, which I'll draw it now in a second. Propanoic acid and benzoic acid. These are used as food preservatives. So this is how we stop food going off. Preservatives. So to draw benzoic acid, again, you start with your basic benzene ring. And it's double bond, single bond, double bond, single bond. And then you've got to make it into an oic acid. So in order to make it into an oic acid, it's got to be a carbon with a double bond and an OH. So this here is your benzoic acid. You got your benzene ring. And of course it's surrounded by your C double bond OH. And this is the part that makes it an oic acid. Okay, we've got to look at some physical properties of carboxylic acids next. So physical properties. I'll draw out a couple of things here and I'll be back to you in 1 second. Okay, so we've got some molecules drawn here. So the first physical property we're going to look at is boiling points as normal. And what we have is we've got two ethanoic acid molecules. Both of these are ethanoic acid. The only difference between the two of them is this molecule on the right has been flipped backwards and flipped upside down. You still have the C double bond O and the OH group as well. So these two groups are lined up against each other. They're exactly the same group. And the reason why they're lined up like that is so we can actually have a look at the bonding that's between them. In a carbonyl group, the oxygen is slightly negative, the carbon is slightly positive. In other words, the electron spends more time with the oxygen. And in the OH group, it's exactly the same thing. The oxygen takes the electron more of the time, where the hydrogen takes it less of the time. So hydrogen becomes positive. The same thing applies in the second molecule. Hydrogen is more positive, oxygen is more negative. Over here, oxygen is more negative, carbon is more positive. And these two molecules come together, and this is essentially what hydrogen bonding is. And the negativity of the oxygen is attracted to the positivity of the hydrogen, because opposites attract, it's magnetic. And then the positive, the hydrogen, attracts with the negative of the oxygen here. This here is what's called hydrogen bonding again. It takes a large amount of energy in order to break a hydrogen bond. So to give you an idea, here is ethanol and ethanoic acid. So ethanol has a boiling point of 78 degrees Celsius, and that's due to hydrogen bonding between the ethanol molecules. When the OHs line up against each other, they attract each other, and you've got hydrogen bonds. However, in ethanoic acid, you don't just have the hydrogen bonds with the OH groups, you also have bonding with the carbonyl group. So this compound here, there's more hydrogen bonding on the right hand side. There's more hydrogen bonding. So the boiling point for ethanoic acid is actually 118 degrees Celsius. So you need a lot more energy in order to break the bonds between ethanoic acid, which you can see here. So you need 118 degrees Celsius to break those bonds and boil it. In other words, turn it from a liquid to a gas. So the next step, number 2, is going to be solubility. And that's the last part of the physical properties. So with solubility, of course, the first one that we're going to look at is water, H2O. And again, when we have something like ethanoic acid, this part of the compound, this part here, is highly polar. And it's highly polar because of two things, the carbonyl group and the OH group. Both of these make it very, very polar. Oxygen itself, or sorry, water, should I say, is also highly polar. And because like dissolves like, that means that ethanoic acid is highly soluble in water. Now, as you increase the length of the chains in ethanoic acid, the longer chains makes this whole molecule. So this particular part here, these carbons here, because it's a longer chain, that lessens the effect of the polar parts. So longer chains means the molecule is less polar, and if it is less polar and you're trying to dissolve it in highly polar water, the later ones and the longer chains may not dissolve in water. Okay? So don't dissolve in water. And this isn't a case of, you know, the first 2 or 3 dissolve and the next 2 or 3 don't. It's not just a switch where it goes on or off. The amount of dissolving it does lessens as it goes along through the carbons. And then, of course, finally, the last one then is organic solvents. So it's solubility in water and its solubility in organic solvents. And carboxylic acid is generally, they tend to dissolve. Tend to dissolve in organic solvents. So that ends that part on carboxylic acids. There's one left, which is esters, and that's going to be in the next part of the video.